So we're going to start our class period today with a couple of general announcements. The first and probably most important announcement, and I know I sent out several emails to specific students yesterday, Sunday night, but there's quite a few of you who have not yet registered for the Connect website, and that online homework is a required part of this course. There are assignments that are due already, and we can't get behind on those because we cover quite a few chapters in this course. The first Learn Smart was already due, and the first homework assignment is due tomorrow night, I believe. So if you're not registered for that, or if you're not already completing the assignments on there, make sure you get on that as quickly as possible. So, second announcement is, as we said it during our first, and for some of you, our only in-person lecture so far this year, that we would be having quizzes on Wednesdays or Thursdays in lecture. Those quizzes are going to continue. So later on this week, we will have our first quiz, and we'll talk more about the format of that on Wednesday or Thursday. Obviously, though, it won't be in the same format as a traditional quiz, but that'll be done online as well. So last time we had just started to introduce the periodic table and some of the information that we find on it. So that's where we're going to continue today. Again, here it is. And as I said, now we've completely filled up the 8th row on the periodic table, and there's now 118 elements. So the next time a new element is discovered, it will end up going here and starting a new row right below francium. And then the periodic table will continue on from there. But last time you may recall that for any element, and we said sometimes we use a notation that looks like this. Where this is the symbol, tells us what element it is. The number up at the top is our mass number, which is equal to the protons, number of protons, plus the number of neutrons. And this bottom number is our atomic number. And that's equal to our number of protons. But if we go back to the periodic table, and we can choose pretty much any element. So let's choose, for example, chlorine. Chlorine is element 17 and has a mass of 35.453. So let's write that down over here. Chlorine, 17, and the mass is 35.453. And that's not coming out very clearly. So the question we could ask here is, how many protons, how many neutrons, and how many electrons does chlorine have? And two of these questions are going to be relatively easy. Because we know that the number of protons are equal to the atomic number, we know that's equal to 17. Because we're dealing with a neutral atom, then we know that the number of electrons also have to be equal 17. But what about the number of neutrons? And in fact, it becomes a little bit more challenging here, because 35.4 is almost halfway between 34 and 35. And we can't have half a proton. That doesn't really make any sense. So we need to talk about what happens when we change the number of subatomic particles within an atom. So what happens is we change the number of subatomic particles. So we're talking about what happens if we change the number of protons, the number of neutrons, or the number of electrons. And we'll look at those each individually because those are three very, very different items. So the first one, and this is by far the most straightforward. What if we change the number of protons? Well, as we said, the number of protons defines what the element is. So if we change the number of protons, then it changes what the actual element is. That's our first one. What if we change the number of electrons? This doesn't change what the element is. This gives us an ion. An ion is a charged species. So if we add electrons, we have a negative ion. If we lose electrons, we have a positive ion. And we have names for these. So a negatively charged ion is an anion, and a positively charged ion is known as a cation. And if you want some help remembering these terms, just think of it this way. A cation, cat, and we know that cats have paws, and so therefore a cation is an ion that is positive. Right, but none of this explains why we have a mass number for carbon or for chlorine here that's halfway between. So what happens when we change the number of neutrons? Here we get what's called isotopes. So these are the same atom, but with a different number of neutrons. So for some atoms, for some elements, there may only be one naturally occurring isotope. Or if there's more than one, one of them dominates. And so we end up with a mass that's still very close to a whole number. And that's actually what happens for carbon. If you notice carbon has a mass of just 12.01. And that's because if we look at the types of isotopes of carbon that are possible and look at how much of each one exists, carbon is made up of just about 99% carbon-12. But let's look at chlorine again. Again, for chlorine, we said the mass is 35.453. So we can look up isotopes and natural abundances. And if we look up chlorine, here's what we find. And if you want to look up any of these, the website Web Elements gives you a ton of interesting information about each element in terms of data and other things like that. If you're ever interested in what some of these, seemingly more obscure elements are useful for, there's actually a lot of interesting information about those as well. But for those, there's actually another website I would recommend. But what you can see here, again, we want to remember that the mass for chlorine is listed on our periodic table as 35.453 AMU. So we can see that chlorine has two naturally occurring isotopes, one with a mass of 35 and one with a mass of 37. And so, again, if we want to think of this in terms of numbers of protons, neutrons, and electrons, we can think of it in this way. So we'll start with chlorine 35. We already know it has 17 protons and 17 electrons. But the number of protons and number of neutrons have to add up to that mass, so this has 18 neutrons. When we go up to chlorine 37, the only thing that can change here are the number of neutrons. So here we have 20 neutrons. Again, 20 plus 17 gives us 37. Again, we know it has to be the number of neutrons that change, because if we change the number of protons, then we change what element we have. If we change the number of electrons, electrons have such small mass that it wouldn't affect the mass of the atom. So it has to be the number of neutrons that changes. So how does this explain this 34.453? Well, we have to take two things into account. One is the mass of any natural isotopes. The second is how much of them we have. So what this number is, our 35.453, is actually a weighted average based on the naturally occurring isotopes as well as their natural abundance. So if we go up to our table up there and we take 75.78% of chlorine 35, and we add to that 24.22% times chlorine 37, we multiply that out and we get the mass that we find on the periodic table. Now it turns out these aren't the only isotopes of chlorine, just the only stable ones. And so on that website I've listed up above, we actually find that there's seven other isotopes, known isotopes of chlorine. You can see there is a chlorine 36, and it goes all the way up to chlorine 43. So chlorine 43 would now have 26 neutrons. But we don't take any of these into account when we're figuring out the mass of the atom. And the reason for that is these isotopes are unstable. Or they're radioactive. So in other words, over time, an atom of chlorine 41 will decay into some other element. Some of them decay very quickly. For example, we can see chlorine-43, the heaviest of the chlorine isotopes, has a half-life of just 3.3 seconds. So what that means is in 3.3 seconds, half of the chlorine-43 will decay into some other element. Whereas chlorine-36 has a much longer half-life. You can see the half-life there. It takes 300,000 years for half of that to decay. And we find elements that have any range of, very, very long half-lives up to extraordinarily short half-lives. And just to show you a couple of sort of the extreme examples, let's bring these up. Alright, sorry, I'm still trying to bring up one of the really short ones. There we go. So if, for example, we look at beryllium, beryllium has a number of different isotopes, but that includes an isotope such as beryllium-6. And beryllium-6 does exist, but as you can see, it has a half-life of 5.9 times 10 to the minus 21st seconds. So again, in other words, it takes 6 times 10 to the minus 21st seconds for half of it to decay. And so that's one of the shortest isotopes out there that exists. And let's just find one that goes the other direction. So here's one that goes the other direction. Hafnium. So hafnium has an isotope 182, and you can see the half-life on that is 9 times 10 to the 6th years. Oops, sorry about that. So it takes an extraordinarily long time for that isotope to decay. And there's others that are even longer than that. Uranium is a very, very good example. So uranium, which has a lot of radioactive isotopes, has isotopes that have half-lives of anywhere from 6 days, uranium-237, all the way up to uranium-238, which has a half-life of 4.5 billion years. But that's why on the periodic table we see all of these very, very different numbers, and all of these numbers that are fractions. And it's okay, again, even though we can't actually have half of a neutron. So at this point, I'm going to end this first video for today. But what you should do at this point is to open up in-class exercise number 3, looking at atomic numbers, masses, and isotopes, and spend a little bit of time working on it, and then we'll come back and continue with our lecture.